Okay. This is field theory. No, I did mention that in QED the charge of the electron changes with distance. Okay. Mass of the electron changes with distance. So, this is what we will do today. Okay. I will follow one method which is follow up of what we done so far. Okay. I like this method and it gives the same result. Okay. I will mention about other method a bit later, but let us just do this method. So, we will normalize both charge and mass. Now, so far I was working with free energy, free energy for spin system. Now, we are going to change the gears and we will work with 5-4 theory with m is the mass. This in fact I have written this before. So, m squared phi squared plus grad phi squared. Now, and plus this is a nonlinear term lambda phi 4 by 6 by 4 factorial, sorry, 24. Now, if you recall, this was R naught, there is a prefactor C naught there for free energy, and lambda was called G. Okay. So, it is exactly same Lagrangian or same free energy. So, we can use lot of the results which we did before. Okay. So, I am going to follow that method which I did with equations, right. I did it in the class. So, I renormalized m square R naught as well as lambda. If you recall this, these two were renormalized. C naught was not changed. C naught remained the same. In fact, that is why C naught is not a factor here. We just remove that stuff. So, these two parameters m squared and lambda will be renormalized following very similar procedure. Okay. Let me say this, we will do only coarse graining, but no rescaling. That is the difference. So, coarse graining, when you coarse grain, I have system at very small scale, right. This is a system. You can think of these are field variables. Okay. Now, when I coarse grain, I get bigger systems. I mean bigger packets. For spin, bigger packets, or for fields I am looking at the system at a larger scale. Okay. I coarse grain further, then what happens? Well, I mean there let us put 9 of them or 16 of them, but now I coarse grain these that bigger blocks. So, what happens to these blocks? The block sizes are increasing. Okay. So, if I just coarse grain not rescale, my blocks are becoming bigger and bigger. Okay. Wilson, what he did or what Wilson did was he after coarse graining he compressed it. So, as a result what happened, these big blocks become a same size as this earlier block. So, system size did not increase, only thing is what we had the parameters or system variables were coarse grain plus rescaled variables. But for today's lecture I will not rescale. So, my system size will grow and grow and grow, and I am going to look at what happens to m squared under this coarse graining. Okay. So, rescaling is not required. Okay. So, let us just follow that trick. I mean, I think that is pretty simple after that. So, the equation, I can derive equation of motion from this. So, I will get this equation of motion. Now, we will set this to equilibrium. Equilibrium means that d by dt of phi is 0. So, I am going to renormalize, I am going to work with this equation. Okay. Now, we work with Fourier space. So, what happens in Fourier space? Laplacian becomes k squared phi k hat, and this becomes a nonlinear term, right. Nonlinear term is convolution. So, lambda by 6 by the factorial 4 which 24, and the 4 came from after differentiation. So, that becomes 1/6, and this one was by you take a stuff functional derivative, you get Laplacian. Okay. Now, this becomes the convolution. So, phi k1, phi k2, phi k3, this is this, k1 plus k2 plus k3 equal to k, right, that we have done it before, k1 plus k2, k3 equal to k. So, like before, I am not going to belabor on this point. Like before, we will separate the variables. For coarse graining, I said let us use a small variable and big variable. I said that if this is scale, then we had k greater and k less. Okay. So, when I coarse grain, I average over these variables and I keep this, retain these variables. Okay. So, this was coarse grain that way. Please recall that discussion which we did before. So, we will do a differential equation. So, the equation is this. Okay. I wrote that before, I mean the previous slide. I did not put a hat here, but okay, this is a, and these are nonlinear term which has become a convolution and delta function. So, we divide phi k into two parts, phi less which is in the for lower wave numbers. So, these are wave number, okay, k, and this is larger wave numbers, and we are going to coarse grain on this, and this was lambda and lambda 0. Lambda 0 is the wave number of the bigger sphere and lambda is the wave number of the smaller sphere. So, I am basically coarse graining on this in d dimensions, okay, and d is will be 4 for the regions which is obvious that at 4 and above the nonlinear term is small in terms of perturbation. So, I can do perturbation, that is the idea that why we use 4, why not 3. It turns out in 3 dimensions the nonlinear term is huge and I can do perturbative expansion. Okay. So, this is exactly same what we did before. In fact, I have taken the same slides, put it here. Okay. And so, this convolution, by the way, this term is well, I am going to look for phi less. Okay. So, I am going to write equation in this regime. So, I am looking for equation for phi less. So, this part convolution has lot of terms, right. So, it could be phi less, okay. I mean this is a product, no. So, I can get k by any combination of k 1 plus k 2 plus k 3. So, this also you should know k vector k 1 like that, k 1 k 2 k 3. So, here all k 1 k 2 k 3 are less than small, okay. So, they are basically in that band, but it is possible that k 1 is huge, okay, and k 2 is also huge, but k 3 is also huge, right. So, that will come here, but sum is k, but k 1 k 2 k 3 magnitude wise can be large. So, that is what you got, but the other possibility is we can have 2 large and 1 small, okay, or 2 small and 1 large. These are 4 possibilities in fact for this. Okay. Only condition is that k equal to k 1 plus k 2 plus k 3 vectorially. Okay. Now, I will do ensemble average, assuming that these field variables are Gaussian, phi greater is Gaussian, that is assumption we will make, okay, which is same assumption done in all field theories, that we assume the field variables to be near equilibrium or equilibrium is Gaussian. Okay. So, what happens to 3 I mean all greater, what happens to them? Because Gaussian odd order it should be 0, right, Wick's theorem, no? All odd order is 0. Next, what happens to, by the way, this one will remain as is, this should not change because this is less, I am not averaging over less variables, these variables are as is. Okay. So, these two are taken care of. What about this? Or let us look at this. What happens to this? 2 less which is not to be averaged and 1 greater. So, less will not average and 1 greater. So, basically averaging will fall here and should be 0 because average phi is 0. Okay. So, that is also 0, but the next one is non-zero term. Well, this is same as that, and that as I said. Okay. So, I missed one. So, the one term which is not 0 is this term, because there are 2 phi graters. 2 phi graters can be non-zero, right. I mean this Wick's theorem says even order things will be non-zero. So, that is what we are going to compute. Okay. So, this is the term 2 greater and 1 less. So, I just rewrote that. Okay. So, I think you should see this equation very carefully. This part I replace, this goes there, and which other term goes there? 2 greater and 1 less, this goes there. So, this cube the triple order term correlations has combination of 2 terms. One is this guy, which is looks very similar to the original equation, right, but this new term which is 2 greater and 1 less, and 2 greater and 1 less I take it to the right hand side. Okay. This clear? No, I just took it to right hand side and I am going to compute this using field theory. Okay. And so, Feynman diagram we write like that, 2 greater and 1 less, these are 5 variables, and in the next slide I have. Okay. So, this is exactly this is right hand side, and so less will come out, less is not to be averaged, this is correlation function, right, this correlation function k1 plus k2 will be 0, right, or k1 equal to minus k2. So, this is exactly this is a second order correlation function. Okay. So, that is written as Feynman diagram, this loop diagram, this is called loop. So, this is C of k correlation function. In correlation function for 5-4 theory is what? Without, well, I mean this linear term. Okay. So, it is perturbative. So, I can use the linear correlation, which is k squared plus m squared. Okay. Well, of course, I need to integrate it dk. So, this is the correlation function. If Fourier space is that, and of course, you will get that one. Okay. So, this is the coming from here, but it is possible that I can go to higher order, one order higher, and so this is what I wrote integral. By the way, this integral is from lambda to lambda naught. I am doing this sum, all I am averaging only the large Wave numbers, not averaging all of it. So, this integral is from lambda to lambda naught. Okay. So, it is done over this shell. This is a procedure of Wilson. Okay, it is very famous procedure, and that is what we do. Now, let us look at T2. So, we can go. So, I have 2 greater and 1 less. In fact, this beauty of Feynman diagram. Okay, Feynman, that is a very nice way to do it. So, 1 less I keep here, 1 less. 1 greater I am going to 1 greater I will keep here. So, let us call it A is here. This B I keep it here, but this C I am going to expand. Okay. How do I expand this C? So, C is 5 greater, no, 5 greater. This is C, 5 greater of k. Okay. So, now, well, what is this value? So, first order, of course, I did that before, two of them become a correlation function, but I say, well, I go to next order. So, remember equation for phi, which is m squared plus k squared phi equal to nonlinear term. Nonlinear, I take it to the right hand side. So, lambda by 6 phi 3 phi's, no, I am not writing k1, k2, k3. So, phi greater is nothing but this is Green's function inverse, right. This is what Green's function is important. Green's function inverse this is gk inverse g naught, linear part of the Green's function. So, we take it to the right hand side, inverse I multiply g both sides, it is an operator g naught of k. I just take, and this is lambda by 6 lambda by 6 phi. Okay. So, this is what how I expand and compute the function to next order. Is that clear to everyone? Okay. So, this is very similar to what you do in quantum mechanics, Born approximation. No. So, you compute this wave function to next order, you might have done this, it is pretty similar idea. So, this is a Green's function. Okay. This is a Green's function g of k, g naught of k, this is g naught of k, and I have 3 legs. Okay. The 3 phi's. So, 2 phi's I keep it less, this is less, 1 greater. You understand, no? The 3 phi. So, these are 2 less. So, this I call it C, D, E. So, this is C, this is D, and E will come from this side, E. Okay. Now, this B and E will come together. So, this is phi of greater of k 1 and this phi greater of some other wave number is S 1 let us say. Now, when I average them, what will I get? Phi greater k 1, phi greater S 1, I will get a correlation function, right, yes or no, but k 1 plus S 1 must be 0. This is the condition, no, the wave numbers must be equal and opposite. Okay. So, this is what we get here. So, 3 less you keep it out, this less, this less and this less are here. 3 legs, this is called 3 external legs are outside, and I got this Green's function is coming from here, this GK1, this Green's function, right here, this is the Green's function, and this is the correlation function, this correlation function here. Okay. It turns out for equilibrium system, the Green's function and correlation function are same. In fact, I should call it G naught, linear Green's function. And what is this one? This is m squared plus k1 squared, and this is m squared plus k2 squared, k2 squared. Okay. And the integral is here, gk1 ck2, but we did that in slightly in the past. K1 and K2 are larger and K is small. So, we can make some approximation, which is always done in field theory. Essentially, we basically we say, well, K1 and K2 are roughly same, and we get K1 m squared plus K1 squared. Okay. So, here K1 and K2 are not same, right, K1 is here, K2 is not here, but under the assumption that the waves to be integrated are much bigger than the waves to be for wave number k, we can get this. So, this I think I did describe it in my earlier lecture, but this is my integral. Now, this overlapping with this, but this is the integral lambda 0 dk 1 by 2 pi to the power d m square plus k square squared. The earlier integral was there was no square, earlier integral was only single power, but this is 2 power, okay, correct. So, I expanded the system up to second order. Okay, now let us look at all the equation, put this all together. So, this is my original stuff, right, this is what I wrote, less. In fact, this equation, if it is equal to 0, then I say, well, I get back the original equation, but it turns out you do not get back the original equation, there is some more terms. So, what are the 2 new terms? One term was this, right, well, I am sorry, this should be m squared and this should be note C naught, okay, this is copied from my previous slides, okay. So, m square plus k square, okay, and the second term is the quadratic term, which is this term. Oh, I forgot to, no, there is a multiplication, that integral dk by 2 power d 1 over k squared plus m squared square lambda to lambda naught. Okay, this part is missing here, this is a term. Okay. So, these are new terms which have come. Now, let us compare how, so these terms we should do something about them, so that my equation, the new equation looks similar to old equation. Now, what should I do to the first term, this one? This is an integral, this is a number, right, and is multiplied by phi less. So, where should I combine it to? I should just add it here, no, because both these terms have phi less k in the front. So, I should just combine it there. Now, this is a number. So, what will happen to the prefactors m squared plus k squared? Which term will it get added to? M squared, right. So, this term is correction to m squared. Okay. So, this is called mass correction delta m squared. It comes straight from the renormalization. Is it clear? I mean, this in fact the idea is very simple, there is nothing very complicated. Okay. So, this is the correction to delta m squared. Of course, I need to compute the integral and then I will get even better equations, but this is a correction to mass. What about this term, second term? Well, This is also a constant, right? So, where should it, what should it, where should I combine this term? Now, you can look at this equation, this part. Okay. So, this is second part. This looks same as this, right? I have multiplied by a constant. I get a new term which is just a constant, and this correction is lambda squared by 4, and this integral. So, what should it correct? So, this getting added to lambda by 6. So, my lambda by 6 is getting a correction with lambda by 6 less, okay, the new one, which is lambda by 6 minus lambda squared by 4 and this integral, right. So, my new lambda is less than old lambda, and how much less? It is this factor lambda squared by 4. Okay. So, these are the correction to what? Lambda is a coefficient of the nonlinear term, okay, and this is called coupling constant. Okay. So, this I forgot to write, coupling constant. So, this is similar to electric charge. Okay. So, this is a coupling, no. So, this is a coupling constant which is coefficient of the nonlinear term. Okay. So, coupling constant is also getting corrected. Okay. So, we just rewrite them, which is here. Okay. So, m squared less is m squared plus this correction, and the lambda by 6 is this. I had written it before, it is just that. So, we just rewrite this part, this one, as lambda by 6 equal to lambda less equal to, I mean 6 will go up and you get 3 by 2. Okay. So, this is my integral, which this is a correction to lambda. It turns out if I go to the left, both mass, this integral is finite and positive. So, when you go to lower and lower wave numbers, my mass is decreasing and my charge is also decreasing. Lower wave number means larger scale. Okay, for this 5-4 theory, you can't say that this will happen for all theories, but for 5-4 theory, both mass and charges are decreasing when you coarse grain. Coarse graining means I am looking at a larger scale. All right. Now, let us do the integral, that is what is left now. So, this will, so I will first worry about the coupling constant lambda. So, what do I do? So, this equation, no, for lambda less is that, okay, right. I mean, now let us do the integral, which I did not discuss in detail when I did this Wilson RG, but I should have, but let us compute it now with more care. Okay. So, this correction is, I just write this part correction as delta lambda. Okay. Now, this dk integral is written as, so this is a sphere, no. So, we write as this integral dk by 2 pi to the power d is written as a shell area, right. In 3D, what do I do? 4 pi k square dk, right, that is what we do. This 4 pi is the radius of the area of the sphere, okay, and multiply by k squared, which is coming from the prefactor. So, in d dimension, what do I expect? So, omega d, in fact, omega d also includes this 2 pi to the power d. Okay. So, this is what I have written it here. This part is the surface area and 2 pi d is this stuff, omega d integral k to the power d minus 1 dk. Okay. That is a formula for the volume element, this volume element, omega d k to the power d minus 1. Okay. So, that is what we have written here, k to the power d minus 1 dk, omega d is outside, and this one I will assume m is much less than k. Okay. Mass is in fact we will see that it is is a value for low wave numbers. In fact, m going to this k going to 0. I also should tell you that k is like momentum, right. h bar k is p in quantum mechanics, and this is all language of quantum field theory. Okay. So, h bar k is, so when k will be also called momentum. We do not have h bar here, but okay, h bar can always be plug in. So, k is the momentum. So, when momentum is 0, which means I am looking at the system at the free system or at large scales. So, that is m. So, m is much less than k, k going to 0 is m. Okay. Now, so we can write this part as k to the power 4, no, k squared squared. Okay. So, this is written here. Now, this integral can be easily computed. This is straightforward. So, what is this? K d minus 5, and that integral is this. Okay. Now, I am doing from lambda to lambda 0. So, pull lambda 0 out, and it is b is, I should write b equal b is lambda naught by lambda is greater than 1. Okay. Now, you can just do the algebra, this will come like that. Okay. Now, please recall that I want d to be 4 or near 4. Okay. So, this guy becomes 1, right, d is close to 4, d is not equal to 4, close to 4, you just keep it close to 4, and this guy becomes what? In fact, it is conventional in field theory that use b is exponential L. I did describe it before. Equations are nicer with L. So, when I put that this object 1 minus b stuff becomes L. Okay. The algebra I will not do it. It is just straightforward. Exponentially you expand as 1 plus x plus that is that. Okay. Now, looks great, no? This is very simple. And lambda d, what is lambda d for d equal to 4? Lambda 4. Sorry, yeah, no, this is omega 4. Okay, not lambda, omega 4. Omega 4 is 2 pi squared d is 4 divided by gamma 2, and 2 pi to the power 4 is 16 pi 4, right. So, this pi 4 will cancel with that, gamma 2 is 2, okay. This gamma function 2 cancels. So, 1 by 16 pi squared. So, this is omega 4. Okay. So, I will rewrite this delta lambda is a correction. So, we write this is a d lambda by dl, right, it can go to the left, no. So, lambda less minus lambda is d lambda. So, d lambda by dl is that, okay, straightforward. Now, we can write L as log of b also, right, L is log of b from here. So, we write this part as d lambda by log of d log b, and this is called beta function. This standard in field theory is called beta function. Okay. So, so far so good, but can we solve for lambda from this equation? Right, it is a simple differential equation, is a in fact not linear, but it is a simple differential equation 1D. So, we solve it. Okay, before I solve it, I need to make one more change. So, here in Wilson theory, I am going from large wave number to small wave number, right, or I am going from small scale to large scale. But in field theory, normally we go from low energy to high energy. So, I am looking at an electron, I am probing it from far, and I am going closer and closer. So, going closer, what does it mean? Going closer, I am not coarse graining, I am doing other way around, I am going closer. So, I am making some, of course, the intuitive argument, but going closer means I am doing reverse of coarse graining. So, L is going from other way around. So, here lambda increases, decreases when you go to small momentum. Momentum is k, okay. I mean, going right now, that is why it is easier to talk in momentum language. I am going to lower wave numbers, no, here lower wave numbers. Low wave number means I am going to larger scales, but I need to do other way around for field theory. So, I go to higher momentum. If I go to higher momentum, then L will change sign, right. So, this full algebra I did not want to do it for other way around, but just simple intuitive argument that lambda increases as you go to larger momentum, the sign will change. So, this becomes a plus sign, okay, that is it. So, great. Okay. Now, I can solve this equation, is bit of algebra, but so d lambda by lambda squared will give you this. Okay. So, just believe me, this is what we get. This is a this is a momentum for lambda 0, lower limit momentum is m, momentum is k, okay, that is this is dimension of k, and at the upper limit momentum is p, just simple integral. Okay, I hope I do not need to do this stuff. Okay, and I can get equation for lambda, which is this. This is my equation. So, my charge, when I go from lower momentum to higher momentum, this is the equation for the charge, which changes with momentum. Okay. Okay, now how does it look? Now, can we relate it to something which we might have studied in other courses? Okay. So, let us go to quantum electrodynamics. I am not going to derive this equation, which was done by Feynman, Schwinger, Tomonaga. Okay. They derived this equation, this object for QED. Okay. And of course, that algebra is very complicated. 5-4 theory is simpler. But for quantum electrodynamics, you need to work with Dirac equation and then Pauli spins and so on. So, it is pretty complicated, but I just take the result. So, this equation was derived by Feynman, okay, for QED, and the equation is not so difficult. The equation is this: beta function for QED is this.